Fermat's last theorem and the quarter cubes rule. Negative Pythagorean quartets of the form d squared equals c squared plus b squared minus a squared. My motto: plain honesty, simple truth, easy understanding, the joy of finding things out for yourself. I included the above infinite sequence of negative Pythagorean quadruples in a previous upload, the title slide of which is shown in the bottom left corner. Gaps in the sequence can be easily deduced from the rules of formation of the quadruples, so that the sequence applies to every integer from 1 to infinity without end. This slide shows the extended series of negative Pythagorean quadruples from 1 squared to 20 squared. The quadruples already known are still in red, and the new deduced quadruples are in black. Ignoring the exponent and considering only the integers in the quadruples, the rules of formation are simply 1. The two largest terms have a difference of 4 for quadruples greater than 3 squared. 2. For any pair of largest terms, the two smaller terms are given by 1/4 the sum of the two terms plus and minus 4. Looking at the short list of 6 quadruples, we note that the difference between the base numbers of the first two terms is always 4, and the sum of the last two terms is given by the product of 8 times an integer, which is always 2 less than the largest base number. The integers are therefore sequential as per the quadruples themselves. Now 17 squared equals 13 squared plus 8 times 15 converts to 17 squared minus 13 squared equals 8 times 15, the difference of squares equation. Since 8 is just 2 cubed, we need only to replace 15 with 8 to give 2 cubed times 2 cubed equals 4 cubed equals 64, and find the two squares x squared and y squared such that x squared minus y squared equals 4 cubed equals 64. 1. The multiplier coloured blue equals 8. Divide by 4 gives us 2. 2. The multiplicand coloured red equals 8. 3. X equals the multiplicand plus 2 equals 10. 4. Y equals the multiplicand minus 2 equals 6. 5. 10 squared minus 6 squared equals 4 cubed equals 64. Observing the difference of squares obtained in Table A, we note that 29 minus 10 equals 19, which is equal to the difference of 3 cubed minus 2 cubed, and 66 minus 29 equals 37, which equals the difference of 4 cubed minus 3 cubed, and so on and so forth. Replacing 2 cubed by the cubes of the other even numbers, we can generate additional difference of squares sequences as shown in tables B, C and D. It is self-evident that the number of difference of squares tables we compute is as endless as the cubes of the even numbers. Notice that 1728 coloured light blue occurs in tables A and B, and 13824 coloured green in tables B and C, both of them with difference of squares solutions for the same number. What we have done is back calculation, insofar as we have determined a cubic to determine the difference of squares in order to calculate the cubic multiplied by a constant cubic. We could determine the first difference of squares in the sequence and use the numerical algorithm given in the following table to find the sequential differences of the cubes and add them repetitively to obtain all the other difference of squares terms. The algorithm calculates the differences for adjacent cubes and is valid for all powers by making the power of the first column 1 less than the power we are evaluating and making the numbers in red equal to the differences of the power n minus 1. If we raise the power of the first column to 3 and replace the red numbers by the blue ones, we would have the differences of the fourth power quartics. We can interchange the two black integers in columns 1 and 2 without affecting the answer. In addition to what we have just shown, we can also produce all the cubes as difference of squares by the method of splitting the square, which consists of dividing the cube by 2 and plus and minus a half for the odd cubes and plus and minus 1 for the even cubes, as shown for 2 cubed and 3 cubed. Also, we can produce every cube as the difference of two adjacent triangular numbers squared, as shown for 6 cubed and 7 cubed. There are infinitely many, yet only a minority of cubes exist as either a positive or negative cubic quadruple, as shown by the two examples for 6 cubed and 12 cubed. The relevance of what we have just done for Fermat's last theorem is simply that the simpleton x to the n equals z squared minus y squared reigns supreme, QED. Alias 1, the difference of two squares equation, 2, the Pythagoras theorem equation, and 3, the quarter squares rule equation. End of video.